Hey guys, Miss Larson here, just reading from our book, The Number Devil, A Mathematical Adventure. I am picking up on page 76 here, and we're going to be talking about a new concept of square roots. So, you recall our hopping game, I'm sure. What we did with the 2 and the 5 and then 10, 10 times 10 times 10 equals 1,000, which we write as 10 to the third or 10,000, or sorry, 10 to the third or 1,000. Because it's faster, right? And when we hop with the twos, we get 2, 4, 8, 16, 32, and so on. As always with our little tricks, till the cows come home. Well then, said the number devil, how much is 2 to the fourth? 16. Pretty good, eh? Perfect, my boy. And now let's do the first hop in reverse, hopping backwards, so to speak. Only when you go backwards this way, you don't really hop. We'll call that step taking a rutabaga, as if we were pulling one of those fine root vegetables out of the ground. So, what is the rutabaga of 4? 2. Right. Taking the rutabaga is the reverse of our first hop. So the rutabaga of 100 is 10, and the rutabaga of 10,000 is 100. What's the rutabaga of 25? 25, Robert said, is 5 times 5, which makes the rutabaga 5. And there he is with a rutabaga. Keep it up, Robert, and you'll be my apprentice someday. Rutabaga of 36. The rutabaga of 36 is 6. Rutabaga of 5,929. Are you crazy or something? Robert shouted. How do you expect me to do that one? Mr. Buckle plagues us with enough dumb problems in school. I don't need to dream about them. Calm down, said the number devil. Little problems like that are what the pocket calculators are made for. Pocket calculator? They're as big as a couch. Be that as it may, you'll notice that it has a key with this sign on it. There's the square root sign, guys. Which means rutabaga. Right, now give it a try. And you enter that into your calculator. And Robert did as he was told, and he immediately read the following off the backrest of the couch calculator. 77. So if you put the square root of 5,929 in the calculator, you get 77. Fine, but now hold on to your hat and try the rutabaga of 2. Again, Robert did as he was told, and he got the following, which is like 1.41421356. It's a very long number. Drat, he cried. It's utter gibberish. Numbers stew. I can't make head or tail of it. Nor can anyone else, my dear boy. And that's the point. The rutabaga of 2 is an unreasonable number. Is there any way of knowing how it goes on? Because I have a feeling it does. Right, you are, but I'm afraid I can't help you there. Taking the number any farther would mean running myself or my calculator into the ground. Wild, Robert said. A real monster. But write it like this, square root 2. And butter would melt in its mouth. Well, let's try something a little less daunting. He drew a few figures in the sand and said, have a look at these. There are the figures. You can see them there. Count up the small boxes inside the squares and tell me whether you notice anything special about them. You can pause the video if you'd like and count up the numbers in the squares and see if you notice any patterns. 1 times 1 equals 1 squared equals 1. 2 times 2 equals 2 squared equals 2. 3 times 3 equals 3 squared, which equals 9. And 4 times 4 equals 4 squared, which is 16. You can see that there at the top of the page. You bet I do. They're all hopping numbers. Right. You see how it works, don't you? Count the number of the boxes inside each square, and you've got the number to hop with, and vice versa. If you know how many boxes the square has, 36, say, and take the numbers rutabaga, you get the number of boxes on each side of the square. So look back at the square. You can kind of think of that. So the square root of 1 equals 1, the square root of 4 equals 2, the square root of 9 equals 3, and the square root of 16 equals 4. Great, said Robert, but What's that got to do with the unreasonable numbers? Well, squares are wily beasts. Never trust a square. They may look innocent, but they can be full of tricks. Take this one, for instance. And he carved a perfectly ordinary empty square into the sand, and then he pulled out a red ruler from his pocket and laid it diagonally across it, like that square in the top. Now, if each side has a length one what? 1 inch or 1 foot? Robert interrupted. It makes no difference, said the number devil impatiently. One, whatever you please. Call it quing or quang, for all I care. Now tell me how long the red line is. How should I know? How long's the red line? If each side of that square is 1, how can you figure out the length of the red line? How should I know? It's the rutabaga of 2, shouted the number devil triumphantly. How did you get that? Asked Robert, who was starting to feel a little overwhelming again. Don't worry, said the number devil. We're coming to it. All we have to do is place another square over it at an angle. He pulled 5 more rulers out of his pocket and laid them in the sand, which made the figure look like this. So you can see what he had originally, and you can see what he just drew. Now, guess how big the red square is? The one at the one at an angle to the black one. I have no idea. The red square is exactly twice as big as the black one. Shift the lower half of the black one into one of the 4 corners of the red one, and you'll see why. It reminds me of a game we used to play when I was little, Robert said. Heaven and Hell, we called it. We'd fold up a sheet of paper into sections, painted black or red, open it into the black, and you went to heaven, and open it into the red, you went to hell. And do you see that is the instance there is twice as much red as there is black? I do. Good. Now, since the area of the black square is 1 times 1 quang, we agreed to call it the length of the side of quang, remember? We can write it as 1 squared. And if the red square is twice as large as the black one, what is its area? 2 times 1 squared, said Robert. In other words, 2. Correct. Then how long is each side of the red square? I'll give you a hint. All it takes is a backward hop. I see, said Robert, the scales falling from his eyes. Rutabaga, you need to take the rutabaga of 2, which brings us back to our original totally unreasonable number, 1.414213. Stop, said Robert quickly. You'll drive me crazy if you keep on with that number. It's not so bad as all that, said the number devil, but we don't need to work it out. Just don't go thinking that unreasonable numbers are a rarity. Quite the contrary. Take it from me. They're like sand on the beach, more common even than the other kind. But there's an infinite quantity of the other kind, the ordinary ones. At least that's what you've been saying and saying and saying. Because it's true, believe me. It's just that there are many, many more unreasonable ones. More than what? More than an infinite quantity? Exactly. Now you're going too far, said Robert in no uncertain terms. I refuse to believe it. More than infinite? Nothing is more than infinite. That's a lot. Malarkey. A lot of malarkey. That's what it is. Want me to prove it? Asked the number devil. Want me to conjure up all the unreasonable numbers at once? No, anything but that. The 9 chain was bad enough. Besides, what kind of proof is magic? Blast, said the number devil. You've got me there. But he didn't seem terribly annoyed. He merely frowned and started thinking hard. I could probably come up with another proof, he said at last, but only if you insist. No, thank you, said Robert. I've had enough for today. I'm beat. If I don't get a good night's sleep, I'll be in for it tomorrow at school. I think I'll stretch out on your calculator if you don't mind. It looks awfully inviting. Be my guest, said the number devil as Robert lay down on the fleecy, furry, couch-sized calculator. You're asleep as it is. You learn best when you sleep. And he tiptoed off so as to not awaken him. There's Robert sleeping on the calculator, which is in his dream. Maybe he's not so bad after all, Robert thought. In fact, he's pretty cool. Robert slept peacefully and dreamlessly late into the morning. He'd completely forgotten the next day was Saturday, and on Saturday, of course, there was no school. Thanks for listening to the end of that chapter, where we now have talked about square roots and unreasonable or imaginary numbers.